Welcome to Dave's Aviation Adventures and Aeronautical Explorations. Today's topic is wind correction and timing for old school holding patterns. Let's focus on the old-style holding pattern like this one at Fredo on the ILS localizer approach at Plymouth, Massachusetts.
A quick review of the altitudes tells us we want an inbound leg of 1 minute below 14,000 feet. Newer RNAV holds like this one at Wybe use a distance rather than timing for the duration of the inbound leg. Let's review the four parts of a fictitious holding pattern in a no-wind scenario. Here the axes are centered on the fix, with the vertical axis labeled Y as magnetic north-south and the horizontal axis labeled X as magnetic east-west. We're holding south of the fix, and our inbound direction is north. We'll start with the outbound turn. Let's remember the radius of the turn formula is R equals V squared over G tangent phi, where phi is the bank angle. That works out to be about 0.44 nautical miles for 90 knots in a 15-degree bank, or a diameter of about 9/10 of a nautical mile. Starting at the fix after you've made the appropriate entry, the first step is the outbound turn. This is a center rate turn, 3 degrees per second, from the inbound heading to the outbound heading. Second is the outbound leg, where the direction, length, and time are set as needed to position the aircraft for the correct inbound leg of 1 minute. In a no-wind scenario, we need no wind correction, and the time and the distance are the same as the inbound leg. And the direction is just the reciprocal of the inbound course. Third is the inbound turn. This is a center rate turn again, 3 degrees per second from the outbound heading to the inbound heading. We use the normal intercept procedures to intercept the inbound course at the end of the turn. Finally, the outbound leg, which, if we've done the proper adjustments to our outbound leg, this should be 1 minute in time, and since 90 knots is the same as 1.5 nautical miles per minute, the length will be 1.5 nautical miles for the scenario, and there's no wind correction since we're in a no-wind scenario.
Now let's talk about wind correction. Correction for wind distorts the track pattern and changes the outbound timing.
You've probably seen diagrams of a lopsided oval like this one from the notebook I kept as an instrument student.
In general, when the wind velocity is greater than 1/3 of the airspeed, it makes it impractical to maintain the pattern and stay within the protected area. So for a small aircraft with a holding speed of around 90 knots, let's work with winds of 30 knots or less.
Let's apply a direct crosswind to the geometry of this pattern. Here the wind is widening the outbound turn to almost 1.25 miles, and it will compress the inbound turn to about 1/2 mile. This is generally true for any significant crosswind, although the amounts may differ, and depending on which side the wind is from, the outbound or inbound turn will be the one expanded or compressed. The challenge is to apply the correct heading and time outbound to connect the end of the outbound turn with the beginning of the inbound turn. A flight computer can give the inbound wind correction and ground speed. A 90-degree crosswind at 20 knots gives a wind correction angle of 13 degrees left and a ground speed of 88 knots.
If you're flying as a single pilot, you probably won't be able to manage this with an E6B. But if you have a calculator-style electronic flight computer or something in your avionics, you might be able to do the calculation. Let's talk about outbound timing. There are a few rules of thumb discussed in textbooks and FAA materials.
One is the headwind-tailwind rule, where you subtract 1 second outbound for every knot of inbound headwind, and vice versa for inbound tailwind. That's a bit complicated. Think outbound tailwind, you're going faster, so less time, so you subtract. Outbound headwind, think going slower, so you add time. Some say to adjust by 2 seconds per knot instead of 1 second. Another rule of thumb is the double half inbound time rule. If your wind is mostly a headwind on the inbound leg, use half of your time on the outbound leg. If it's mostly a tailwind on the inbound leg, double the time and use twice the inbound time on the outbound leg. And if it's mostly a crosswind on the inbound leg, use that same time on the outbound leg. Think headwind half, tailwind twice.
Finally, we come to wind correction, and there is only one rule that I have seen in the conventional literature, and that is to triple the inbound wind correction and apply it in the opposite direction. Some sources say to double it instead of triple. Well, it has always bothered me that there are so many rules around this, and even similar rules differ quantitatively. Is it 1 second per knot of tailwind or 2? Is it triple wind correction or double? To help me get some insights into this, I modeled holding pattern wind drift and turn drift in a Python program, and the results are interesting. In fact, the lopsided oval that I showed previously came out of this model.
We start with looking at the inbound leg. And the inbound leg, we have a 1 minute time, we have a wind correction of 13 degrees left for an inbound heading of 347, a ground speed of 88 knots, and a length of 1.47 nautical miles. Then we can use that information, plus the wind drift, plus the turn drift, to compute the outbound leg. And the outbound leg gives us a time of 72 seconds, a track of 204 degrees, wind correction to the track of 12 degrees right. That means that relative to the course, which is the reciprocal of the inbound heading, our course, so-called, is 180, but our track that we want to actually fly is 204. So we already have a difference of 24 degrees between the course and the track. And then we apply the wind correction to that, because it needs its own wind correction of 12 degrees right, for a total of 36 degrees, which is we'll call it the applied wind correction to the reciprocal magnetic course, for a final result of 216 degrees as our outbound heading. From there, it's a matter of just computing the turns. So we're turning from the inbound heading of 347 to the outbound heading of 216, and that gives us a change of about 228 degrees at 3 degrees per second. It's 76 seconds, and we have an inbound turn for the remaining 3 degrees per second to get back to the inbound heading of 44 seconds in 131 degrees. That means the nose of the airplane has completed a total of 360 degrees in a turn, and we've arrived back at our holding fix.
I went and tabulated this data for winds ranging 360 degrees around the inbound course, and what I found does support the rules of thumb I mentioned earlier.
In this case, the leftmost column is your relative magnetic wind, and in the rightmost column we have the average outbound time for that group of winds. If the aircraft is facing mostly headwind on the inbound leg, then our average is about 22 seconds. Mostly crosswind, 73 seconds. Mostly tailwind, 123 seconds.
So we do have support for the headwind half, tailwind twice rule, with the crosswind time a little bit longer than 1 minute. Another finding is that the wind correction angle for the outbound leg varies pretty widely, and if I take a ratio of the outbound to inbound wind correction, it falls around 2 to 3 for most relative wind angles. If we graph this out,
we get an interesting sawtooth graph showing the actual wind correction angle outbound through the range of different relative winds.
If we graph the ratio of outbound to inbound, we get a shallow bowl shape.
And of course, we have a dropout at 180 and at 0 because we can't do division by 0 in those cases.
But an interesting point that came up was a scatter plot
of the inbound wind correction angle on the x-axis and the outbound on the y-axis. And it gives this very interesting propeller-shaped model. And what I notice is that if I do a straight line through the graph and compute the slope of that line, it comes out to about a -3 slope.
And that -3 struck me because that goes back to the triple wind correction and the opposite direction rule. What about our rule of adding or subtracting seconds based on so many knots of wind velocity? Looking at this data, we can see that subtracting 2 seconds per knot of headwind seems to give us good correlation. For example, 60 minus 2 times 10 gives us 40, which is close to 38. 60 minus 2 times 15 gives us 30, which is exactly 30. 60 minus 2 times 20 gives us 20, close to 22. And then 60 minus 2 times 25 gives us 10, which begins to diverge from 17. For tailwinds, the factor of 3 seems to be best. We have 60 plus 3 times 10 gives us 90, close to 87. 60 plus 3 times 15 gives us 105, close to 104. 60 plus 3 times 20 gives us 120, close to 123. And then it diverges at 25, where 60 plus 3 times 25 gives us 135, whereas the model gives us 144. So those are some of my insights. I'll post a video to put theory into practice, because as we all have seen so often, in theory and practice are the same, but in practice they're different. Until then, this is Dave, encouraging you to stay current and proficient.